Hello everyone and welcome to this lecture. In the last lecture, we have seen these positive semi-definite matrices. We have seen that these matrices have non-negative eigenvalues and it makes them very useful. Okay, and towards the end of the lecture, we have seen how to, for a given positive semi-definite matrix, if it is given in some partition form where there are blocks, okay, what will be can we actually give a bound on the largest eigenvalue of the bigger matrix in terms of the largest eigenvalue of its block. So we have seen one result and the result was this. So let me write that result to begin with for this lecture. So the result was this, right? So we have already proven this, but let me again write them and then we will try to modify this result. Okay, so yeah, so let B be a positive semi-definite matrix, semi-definite matrix, semi-definite matrix, okay, and partition as follows, partitioned as follows. Okay, so suppose this is B matrix and it is partitioned as B11, B12, B21, B22. Then we have seen that where B11 is some square matrix and so B22 will also be square matrix, where, let me write it clearly, where B11 is P cross P for some P. Okay, then the largest eigenvalue of B is always less or equal to the largest eigenvalue of B11 plus the largest eigenvalue of B22. Okay, now in this lecture we begin with a generalized result of this. Okay, so suppose if I ignore, instead of this, suppose positive definite, if I write just symmetric matrix, let B be a symmetric matrix, symmetric matrix, and then we can indeed write this result as beta 1, in fact this. For any symmetric matrix, partition as follows, where B1 is some P cross P matrix, then the smallest eigenvalue plus the largest eigenvalue is always less or equal to the largest sum of largest eigenvalue of its blocks. Okay, very good. So this is in general. So let us prove this and we will make use of positive semi-definite here somehow. Okay, so proof. So proof is this. Okay, now proof is, so what do you think about this matrix? Suppose B is this matrix, right? B, what do you think about if you remove from B, if you subtract this matrix, lambda 1 of, maybe let me write it more precisely, lambda 1 of B matrix times identity matrix. What will be nature of this matrix? Okay, this matrix will be positive semi-definite matrix. Why? It will be positive semi-definite matrix, but why? It is easily followed from spectral theorem. Remember, you can write B as maybe some diagonalization, you write the diagonalization form of B, okay, and on the diagonals are the eigenvalues, okay, and you are subtracting from that eigenvalues the lambda, and which is the smallest eigenvalue, right? So if you subtract that, rest of the eigenvalues will be always basically non-negative eigenvalues. Okay, and we have seen that what when the eigenvalues of a matrix are non-negative, symmetric matrices are non-negative, then this matrix has to be positive semi-definite matrix. Okay, so easily followed from follows from spectral theorem. spectral theorem. Okay, very good. Now what? Okay, now since this is a positive semi-definite matrix, okay, so now we can make use of the result we have proven towards the end of the last lecture. So in a way it gives that the lambda 1 of, so this, what will be this, let me write this. So b lambda of bn is nothing but, if you in matrix form, this will be b11 minus lambda n of b, at times the identity matrix here, the p, it is p cross p, right? Okay, so very good. And then this is b12, very simple, b21, then b22 minus what, lambda n again of b, but now here the matrix will be n minus p. Okay, you can p cross p or just p, it's okay. Very good. Now make use of the last result of the last lecture. Okay, so that means the lambda 1 of this matrix, because this is positive semi-definite matrix, is always less or equal to lambda 1 of b11 minus lambda 1 of b identity, so I will write this p, plus lambda 1 of b22 minus lambda n b I n minus p. Okay, very good. Now next thing is, what are the eigenvalues of this? Remember, this is nothing but a diagonal matrix, where on the diagonal there are only lambda and lambda and lambda and lambda n. So this is nothing but lambda 1, this quantity is net lambda 1 of b minus lambda n of b. Very simple, right? Because this is nothing but a diagonal matrix, so constant where the entries are all lambda and b. Okay, this is less or equal to, similarly here we can write lambda 1 of b11 minus lambda n of b. Again, the same logic. Again, now let me write plus, here it will be lambda 1 of b22 minus lambda n of b. Very good. Now you can actually cancel these. So this result is, this implies that lambda n of b, so 1 lambda n is there, so I will take it here, which is less or equal to lambda 1 of b11 plus lambda 1 of b22. Very good. So we have now proven this result. Okay, very simple, but it will be utilized shortly in proving some other result in terms of where there are more partitions, and these partitions are in some special way. Okay, so we will utilize this result. Okay, so, and this is for any symmetric matrix, by the way. This is all any symmetric. No doubt, for the proving purpose we have made beautiful use of positive semi-definite here, but this result holds for any symmetric matrix partition in this form. Okay, now let us go to another result. Okay, and we will see use of this result in when we will prove some bounds on chromatic number of graph. Okay, so let me state the next result. Okay, so next result is this. So theorem. Okay, so now let B be a symmetric matrix, partitioned as, now there are many parts, partition as following. Okay, so let me partition this matrix. So on the diagonal now there are 0 blocks. Okay, so this is 0. Suppose b12 up to b1k. So now there are k blocks here. Then similarly here this is b21, this is 0, and so up to b2k, and keep on going here. So let me make bigger one. So bk1, and then you go here till, and this will be, maybe I can write bk2 here. So this will be 0. Okay, so basically it says that on the diagonals there are 0 blocks and rest of the blocks maybe some general blocks. Okay, in that case the lambda 1, so this is as b equal to this, so lambda 1 of b plus k minus lambda, smaller lambda, the smallest eigenvalue of b is this, always gives this. Okay, it always less or equal to 0. Okay, why this happens? Why this happens? So let us read the statement again. So let b be a symmetric matrix partitioned as this. So there are kind of k blocks, k cross k, you can assume blocks. Then the eigenvalue of the bigger matrix can be, the bound is kind of lambda 1 of b plus k minus 1 times the smallest eigenvalue. The sum of these two quantities is always less than, basically non-positive. Okay, so proof. Okay, very good, proof. We will use a very common technique of proof. We will prove it using induction on k. So we will prove it using induction on k. Now remember, when k equal to 2, this by default, for k equal to 2, this is very simple, right? It is easily followed. So in that case, for k equal to 2, b will be what? Nothing but this, right? 0, b1, b2, 1 and 0. In that case it is easily, right? So the lambda 1 b is, and now k is 2, so this will be 1, so plus lambda 1 lambda n, sorry, of b is always less than 0, because these are diagonal, so diagonal entries are 0, so all the eigenvalues are 0. So this follows from this result. Okay, so because this will be 0 plus this will be 0. Okay, now assume that induction hypothesis, assume that the second step, assume that the result holds for k minus 1, some k minus 1, and then we will prove that it also holds for any k. Okay, very good, basically k. Okay, very good. So now from b, so b's structure is this, right? B's structure is what? This. So there are zeros, so b12 up to b1k, then b21 zeros up to b2k, then bk1, bk2 up to this will be 0. Okay, now assume a sub matrix of B where the last row of blocks and the last column of blocks is not there. So basically assume that this matrix. Okay, so this part, basically this part, call it C. Suppose this matrix is C. Okay, basically C, if you see that the last C is the resulting matrix after removing last row and last column of blocks. Okay, so blocks. Okay, very good. Now if you see that, suppose this matrix is C. Now C is what? C is k minus 1. So there are k minus 1 blocks, right? So by induction hypothesis, okay, we can write that the lambda 1 of the largest eigenvalue of C, okay, and then because there are k minus 1, so basically this k minus 2 here will be, because the state there are k minus 1 minus 2, then maybe now lambda minimum, let me write up lambda minimum of C. Okay, so C, okay, so largest eigenvalue, and then lambda minimum of C is always less or equal to 0. This is by the induction hypothesis, right? So induction hypothesis result is 2. There are k minus 1 blocks, so here it will be k minus 2. Okay, the smallest, so everything is going very, very fine. Very good. Now the next thing is, we can also in fact due to because B is symmetric matrix, so we can actually treat this as some C, then there are blocks, then again block, and then so we can also write the lambda 1 of B, okay, plus the lambda n of so basically now I am making use of this theorem, okay, making the, let be a symmetric matrix. So lambda 1 of B plus lambda is always less or equal to this quantity, right? Now this quantity here will be C and this will be 0, okay? So now I am treating this as C, so basically now another thing could be, so lambda 1 of maybe I have not written somewhere, okay, very good. So lambda 1 of B plus lambda n of B is, okay, that's what I was afraid of, because let me, sorry about this. So okay, very good. Okay, so lambda 1 of B plus the smallest eigen or lambda n of B is always less or equal to lambda 1 of C, because now you treat this B as a 2 cross 2 big blocks, okay, plus this block, right? So but it is 0, so it is, I mean, plus 0, so nothing here, okay, very good. Now using these two equations, suppose let me call it 1. So what we can conclude is, we can in fact conclude that lambda 1 of B plus lambda n of B, okay, and then plus k minus 2, the minimum eigenvalue of C is less or equal to 0 from here, because lambda 1 C will cancel with lambda 1 C here. Okay, very good. Let me call it 3. Very good. Up to here this is fine. Okay, but now you see that due to Cauchy-Interlaced theorem, we can always see that the smallest eigenvalue of C is always greater or equal to the smallest eigenvalue of B. Okay, so using Cauchy-Interlace, now next using Cauchy-Interlace, okay, the lambda basically lambda minimum of C is always greater or equal to lambda n of B. Okay, so this is from Cauchy, because C is a principal submatrix of B. Okay, very good. So now let me call it 4. Now I think the result is very, very apparent. Okay, so lambda n is always less or equal to lambda min, right? So if I replace lambda min by lambda n right here, so from basically using 3 and 4, okay, we can now deduce. So we are replacing lambda n for lambda min. So basically this quantity will be more lesser, right? So basically now lambda 1 b plus lambda n b, okay, plus k minus 2 this lambda n b, okay, is still less or equal to 0. Okay, very good. So now what? So now we have proven it. So lambda 1 of b plus k minus 1 lambda n of b is always less or equal to 0. So we have proven this. Very, very simple result, I would say, but it will be very useful when we will be giving a bound on the chromatic number of graphs. Okay, so I hope you understood this. Okay, so we will make, so let me recap. So what we did, so we gave actually two kind of partitions. In one partition there were, it was for all symmetric matrices, okay, where diagonals may not be 0 blocks. In that case we have seen that lambda 1 plus lambda n of the bigger matrices can be written as, is always basically less or equal to the sum of largest eigenvalues of the blocks, right, diagonal blocks, okay. And then there was another result where now there are many blocks, but on the diagonals there are zeros. In that case the number of blocks minus 1 times the smallest eigenvalue, and if you add this quantity with the largest eigenvalue, the result is always non-positive, okay. So thank you very much, okay, and see you in the next lecture for its application. Yeah.